Okay, so last time we have looked at what the Weierstrass phi function is, which is essentially the basic meromorphic function that you can define on a torus. So let me recall that. So our usual notations were tau was a complex number in the upper half plane. So this is a set of all complex numbers z such that imaginary part of z is positive, and we associate to tau a torus, complex torus. How do we do that? We define the lattice L of tau. This is the set of all m plus n tau, where m and n are integers, and your torus is just gotten by going modulo this lattice. Okay, so you have the map, the natural projection from C to C modulo the lattice, and this is what is called as the torus associated to tau, T tau, alright, and of course this map is pi sub tau, and of course so this quotient is the set of equivalence classes where the equivalence relation is two complex numbers are declared equivalent if their difference is an element of this form. Okay, another way of saying it is that each element of L of tau acts as a translation on the complex numbers. Okay, and if you go modulo that action, okay, so this is an abelian group which is just isomorphic to Z cross Z. Okay, and this acts on C, and this is precisely the set of orbits. Okay, and we know that this is a universal covering with the deck transformation group equal to the fundamental group of the torus, which can be identified with the L of tau. Okay, yeah. So the point is we defined the Weierstrass phi function. So the Weierstrass phi function was defined, so phi of z, this is phi sub tau of z. So this was a Weierstrass phi function that was defined on C union infinity. I mean, it's defined on C with values in C and in infinity, in the sense that it is a meromorphic function. So it is it's a meromorphic function with precisely a double pole at each point of this lattice, okay, with sum of residues 0. Okay, and we had a series expansion for the Weierstrass phi function, which was 1 by z squared plus summation over omega in the lattice omega not equal to 0 of 1 by z minus omega the whole squared minus 1 by omega squared. So we saw that this series converges uniformly on compact subsets outside points of this lattice, and at each point of the lattice, of course this is at each point omega of the lattice including omega equal to 0, this has a pole of order 2, okay, and there are no other singularities, so it is a meromorphic function, and so this function is a meromorphic function, and it has been normalized so that the Laurent expansion at the origin has singular part 1 by z squared. Okay, so that was a normalization, and we also showed that this Weierstrass phi function is a doubly periodic function. So it is what is called an elliptic function. It is a doubly periodic function which is meromorphic, in the sense that you know, if I replace z by any element by translation by any element of this lattice, I get back I get the same value. So 1 is a period for the Weierstrass-Zwief function, and tau is also a period for the Weierstrass-Zwief function. That means phi of z plus 1 is also phi z, from which you can inductively deduce that phi of z plus m for any integer m is also phi of z, and tau is another period, and phi, which means phi of z plus tau is phi of z, from which you can deduce inductively that phi of z plus n tau is also phi of z, and if you put both together you will get this. Okay, so we proved this last time. Of course m and n are of course m and n are of course integers. Okay, and it is assumed that z is not one of the lattice points. Okay, because at the lattice points the function is not defined, it is a pole, right. As z tends to any lattice point, you know that this quantity goes to infinity, and that is the reason why we write this map as a holomorphic map into C union infinity, which is the Riemann sphere given the you know, the natural complex structure on the Riemann sphere, okay, that we have already seen. Okay, so well, we got the Weierstrass-Zwief function because we were searching for some functions on the torus. Okay, and we realized that we could not have holomorphic functions on the torus with complex values because they will reduce to constants. Therefore we had to allow poles, and then we realized that such a function, if you have such a function defined here, if you compose it with pi tau, you will get a function on top. So you will have a function on top, and that function has to be that function should be periodic with period 1 and tau. So functions on the torus will give rise to functions on the complex plane which are doubly periodic. Okay, and conversely a doubly periodic function on the complex plane with periods 1 and tau will define a function on the torus. Okay, and then of course holomorphic functions are not allowed, so you are forced to allow I mean you are forced to allow singularities. I mean by holomorphic functions I mean holomorphic functions which are not constant. Okay, and then we saw that the easiest thing we could do is to allow for pole of order 2 at each lattice point, because you cannot have a simple pole because sum of residues will be 0. Okay, so you cannot have a simple pole, so we had to have pole either you had to have a pole of order 2 at each lattice point with sum of residues 0, or you must have allowed for 2 poles with cancelling residues, so that the sum of residues is always 0. Okay, so finally we got this Weierstrass-Zwief function. Okay, and now what is the aim of this lecture? So you see, let me again recall why we are doing all this, so that you know we get the broad picture as I explained in an earlier lecture. See, our aim was to show that you know on the upper half plane, if you go modulo the upper half plane by the unimodular group PSL to Z, okay, these are Mobius transformations of the form Z going to AZ plus B by CZ plus D with ABCD integers, and AD minus BC is actually plus or minus 1, right, and we have already seen how this can be made into a Riemann surface. Okay, and our aim is to show that this Riemann surface is actually isomorphic to C. It's actually isomorphic as a Riemann surface to the complex plane. Okay, so that means you will have to find an isomorphism of this Riemann surface, okay, with the complex plane. Of course you will recall that trying to get this Riemann surface used the fact that we realize that even though PSL2Z has fixed points in its action, it was acting, we were able to prove that it acted properly discontinuously, and the region of discontinuity contained U, okay, and therefore that you can go mod this to get a Riemann surface structure on the quotient, so that this map becomes holomorphic, okay, in particular it becomes a map of Riemann surfaces. And also we also noted that over every point of view, given a point of view where where there is a non-trivial stabilizer for this group, we noted that was a point of ramification, okay. So this is a ramified cover, okay, but the point is we also next wanted to show that this is isomorphic to C. So that means that you have to construct a holomorphic function on this, which whose image is C, okay, and which is injective and which is surjective, okay. So essentially you want to have functions on this, alright. So you want an isomorphism of this with C, and well I'll let me call this as for the moment let me call this as J, alright. So I want to construct this holomorphic function J, alright, which is an isomorphism of this Riemann surface with C with a complex plane given the natural Riemann surface structure. So you see, but of course, you know, constructing a function like this is would mean in particular that you have a function like this, okay. It will mean that you have a function like this, okay. Suppose I call this function as say J tilde, alright, then and then this diagram commutes, namely this arrow is just this composed with this, and since this is also holomorphic, that is also holomorphic, so you are having a holomorphic map from the upper half plane to C, okay. And the fact that this holomorphic map goes down to a map below it should tell you that this map J tilde is going to be constant on orbits of PSL2Z, okay. So trying to construct any function here, okay, is the same as trying to construct a function on the upper half plane which is constant on PSL2Z orbits. But we have already seen that all the elements in a PSL2Z orbit, they correspond to exactly to holomorphically isomorphic complex tori. So we have already seen that this can be identified, okay, with the holomorphic isomorphism classes of complex tori of the form T sub tau. And in fact, you know, this map is none other than send a tau in the upper half plane to the holomorphic isomorphism class of the torus defined by the tau. So this pi is just the map, pi of tau is just, you take T tau and then you take this, I put the square bracket to say that this is a holomorphic isomorphism class, okay. So if you believe that you want to get a function here, you have to find a function which is constant on holomorphic isomorphism classes of tori, alright. But usually a function which is constant on holomorphic isomorphism classes, okay, in general if a function is constant on isomorphism classes, it is called an invariant, because it is something that does not change if you change the isomorphism class, okay. So the moral of the story is that somehow you are trying to find invariants for complex tori, okay, and therefore you see these invariants for complex tori should depend on the geometry of the tori, okay, and therefore if you believe the philosophy that, you know, the geometry of a space is controlled by the kind of functions you allow on the face on that space, then you will see therefore that you are led to search for functions on the tori, okay, and that search is what led us to the Weierstrass V function, okay. So somehow I will have to use the Weierstrass phi function to get hold of a holomorphic invariant, okay, for the torus, that is I have to attach to each torus a complex number, okay, such that this complex number will not change if the torus is changed up to holomorphic isomorphism, okay. And how do I change the torus by holomorphic isomorphism? I do that by simply replacing tau by another element which is gotten from tau by a unimodular transformation, okay, an element of this group, right. So this is the story of how we got the Weierstrass phi function, and now what I need to know is so somehow I will have to, using this phi function, somehow I will have to so I have got the function, I have got a function, a nice function on each complex torus, somehow I have to use it to produce a function on the upper half plane which is going to be invariant under the action of PSL2Z, okay. So the key to that is a beautiful differential equation satisfied by the Weierstrass phi function, which is what I would like to prove in this lecture, okay. So that differential equation is of utmost importance also in showing that every holomorphic I mean every complex torus like this actually has an algebraic structure, okay. So that will also come out as a result of that differential equation. So let me state what the differential equation is, okay. So I'll just say that if you want a j here, you want a j tilde above, okay. So let me draw a line here. We shall prove that the Weierstrass phi function satisfies the following differential equation, So what is the differential equation? Let me write it down. So the differential equation is the following. It is so it is derivative of tau, derivative of p tau of z, the whole squared is equal to 4 times p tau of z cubed minus g2 of p of z, p tau of z minus g3, okay. So this is the differential equation, okay. You can see it is this involves the Weierstrass phi function and its derivative, so it is an ordinary differential equation, and you can see that this is a first order differential equation, and you can see this is of degree 2, alright. And what are these g2 and g3? These g2 and g3 are functions of tau, okay. So what is this g2? See, g2 is, I will write it down, we will compute it and tell and explain what this is. We will see what this is. So this g, so this 60 times g2, I am just referring to my notes so that I do not make a mistake in writing things down. So it is 60 times sigma summation over all the lattice points of 1 by omega power 4, okay. So g2 is this quantity, alright, and so where, and g4 and g3 is summation is g3 is 140 times summation over all the lattice points different from 0 of 1 by omega power 6. Okay. So you see that see G2 and G3 they depend on summation on these summations, okay, and these summations depend on tau. So you must realize that G2 and G3 themselves depend on tau, okay. So G2 and G3 are not just some constants, they depend on tau if you think of dependence on tau. And why should you think of dependence on tau? Because you must always remember that you must think of tau as varying over the upper half plane. So therefore you are trying to find an invariant as tau varies, you are trying to find an invariant for T tau, okay, that is a quantity that does not change if you change T tau, or that is if you change tau by an element of PSL2Z, okay. So this dependence on tau should never be forgotten, okay. So this is a differential equation. Now let me point out one thing immediately. You can see that this differential equation, if you call P of z as a variable x and P prime z as a variable y, then this differential equation becomes the algebraic cubic equation y squared is equal to 4x cube minus g2x minus g3, okay, that is an algebraic cubic equation, okay, it is the equation of a cubic, and that is the first evidence to show that a complex torus has an algebraic structure. So it is actually what is called an algebraic curve, and that algebraic curve is called an elliptic curve, and an elliptic curve will generally have an equation of this form: y squared is equal to 4x cube minus some constant into x, I mean plus some constant into x plus another constant, okay. So the point is, the beautiful thing is that doing so much of analysis and calculus and getting this differential equation helps you to finally say that your object is algebraic, okay. So we will see that also. So let me try to explain how we get this, how we prove this differential equation. So the key to proving this differential equation is to actually look at it, look at the Laurent expansion at the origin, okay, and well the Laurent expansion of the origin for the phi function, okay, we know pretty well that the Laurent expansion of the origin at the origin has this as the singular part and this will be the analytic part. Now the point is that you should write this analytic part in a nice way, okay, so that you can deduce this relationship, okay, and the one way to do that is to first get an antiderivative for the Weierstrass phi function, okay. So which is what we will do first. So let me make the following remark. So the first remark that I want to make is, well, you take yeah, so you see the function so the usual notation is zeta of z. So zeta of z is defined as 1 by z plus summation over elements of the lattice which are not 0, and I put 1 by z minus omega plus 1 by omega plus z by omega squared. So I look at this function, and the claim is that this function is an antiderivative for the phi function, for in fact for minus p tau of z, okay. So let me explain why this is correct. So the first thing is you take the phi function, okay, and look at each term here in the series that defines the phi function. Okay, look at each term. So let's call each term as f sub omega of z. So f sub omega of z is for me 1 by z minus omega the whole squared minus 1 by omega squared. Okay, now this is it's clearly an analytic function except for z equal to omega, the particular point z equal to omega, which is a lattice point where it has a pole of order 2. Okay, now of course you can integrate this function, alright. If you integrate this function over, let's say, any path gamma, okay, which is a path, so you see so this is a complex plane, okay, and I choose z to be a point which is not in the lattice, okay, and what I do is that I choose a path gamma from the origin to z and make sure that the path does not pass through any lattice points. Okay, gamma does not pass through any lattice points, that is, you know, points of L of tau. Okay, you take such a path. Okay, so and you try to, suppose I integrate over gamma over that path of suppose I integrate this f omega z, okay, dz. Well, this is, if I you can see that this is integrating from 0 to z of this quantity 1 by z minus omega the whole squared minus 1 by omega squared and d z. Okay, well, I mean, if you want to be a little bit more careful, then maybe you should call this the z inside the integration as a different variable because my upper limit is also z. Okay, so that shouldn't confuse you, right. Well, if I integrate it, you know what I will get is I will get minus 1 by z minus omega minus z by omega square. Okay, this is what I will get, plus of course I will get a constant. Okay, this is what I will get if I naively integrate it, but you have to be careful because this naive integration is correct only when the integral does not depend on the path. Okay, now the fact is that the integral does not really depend on the path. That is because, you see, if I replace this path by another path, so of course the path has to be directed, so I am going from 0 to z. Suppose I replace it by another path gamma prime, okay, suppose I replace it by another path gamma prime, and also make sure that gamma prime is also not going to pass through any lattice points. Okay, then I claim the integral over gamma is the same as the integral over gamma prime. That is because, you see, the integral over this closed path, that is gamma prime followed by gamma inverse, will actually, the integral of this function will be, by the residue theorem, it will be 2 pi I times sum of residues of this function. Okay, and well, there are two possibilities. If omega is inside, if omega is not inside, then anyway there is no problem. Okay, then the function is analytic in this region inside and on the boundary, and therefore the integral does not depend on the path. On the other hand, if omega is inside, okay, then it will be 2 pi I sum of residues at that point, but sum of residues is 0, because, you know, this is the reason why we put this in the expression for phi of z is because we wanted a double pole with residue 0. Okay, therefore this naive integration is correct. Okay, so you can see that therefore, you know, you can see that minus of this, which is 1 by z minus omega plus 1 by omega plus z by omega squared, is already these two terms here. Alright, now the only other thing is to worry about the summation. So you see that so I just recall a result that if you have a sequence of functions okay, which are defined on a path, okay, and suppose the sequence of functions converges uniformly to a function, and suppose each of these functions in the sequence is integrable, then the if you integrate each of these functions and then take the limit, that will be the same as taking the limit and integrating over the path, okay. So in other words, so long as a sequence of functions converges uniformly on a path, okay, it will you can interchange limit and integration, okay, and the same argument applied to partial sums of a series of functions which are each of which is continuous, okay, will tell you that you can integrate a series of functions term wise, okay. So so long as the series of functions converges uniformly, and we know that the Weierstrass V function actually converges uniformly on compact subsets, we proved that last time, okay. Therefore I can literally integrate this function over such a path, okay, and I can, so the integral over the summation can be taken as summation of the term wise integration, that is because of uniform convergence, and if I do that, this is what I will get, this is what I will get, okay. So I am sorry, I am not integrating this, but I am integrating this, okay. So what I am saying is that if I, so you see, so let me write that down clearly, p tau of z minus 1 by z, if I take this quantity and integrate it from over this path, alright, then I claim that so this is going to be integral over summation omega in the lattice omega not equal to 0 of 1 by z minus omega the whole squared minus 1 by omega squared, okay, and of course I will get a dz, alright, but you know that this integration and this summation can be interchanged because of uniform convergence on compact subsets. In particular, the uniform convergence will also hold on any path, which is of course any path is a compact subset, okay, because it is both closed and as well as bounded, alright. So you can interchange this summation and integration and get that I can write it like this, and I can write integral over gamma 1 by z minus omega the whole squared minus 1 by omega squared dz, I can write this, okay, and this is just integral of f sub omega of z dz, which turned out to be this. So finally what will happen is that you will see that this is going to be, this will be summation over omega in L of tau omega not equal to 0 of well minus yeah, so I will get minus 1 by z minus omega minus z by omega squared, okay, plus a constant, this is what I will get, okay, and you see the net effect of all this will be that so you see the only thing that I will have to do is worry about I will have to worry about what constant I am going to add here, okay. So what that constant can be uniquely fixed by assuming that the integrated function is an odd function of z, okay, putting the condition that the antiderivative is odd, is an odd function of z makes the constant well, the constant will become 1 by it's going to become so this constant will be minus 1 by omega inside the summation. Okay, so if you do that, what you will get is that you will get this function. Okay, you will get this function defined in this way with this constant term 1 by omega coming here. Okay, and this constant term has been added so that this function which is the antiderivative of the Weierstrass phi function is an odd function. You see, because if I say change z by minus z, this will change by a minus sign, of course there is no problem, and this will also change by a minus sign. Okay, the only problem is with these two terms. You see, if I change z by minus z, okay, then if I want to push that minus outside, then I have to change omega to minus omega. Okay, therefore you must realize that this constant has to be so this constant has to be 1 by omega. Okay, I mean if this constant is 1 by omega, okay, then if I change z to minus z, I can pull out a minus sign provided I change omega to minus omega. Okay, and changing omega to minus omega in the lattice is not going to change the sum, alright, but then changing omega to minus omega allows me to pull a minus out of these two terms, and there is already a minus coming out of this term and that term, so I can pull a minus out throughout, therefore this function becomes an odd function of z. Okay, so the condition that this is an odd function of z fixes this constant, okay, inside the summation, and you of course see that if I differentiate this, I will get minus of the phi function. Okay, so also yeah. So let me say that zeta prime of z is, well, minus of this is the phi of z. Okay, this is the phi function, right, and well in principle I should have I should keep remembering the tau, because but for the moment let me not let me drop the tau, alright, in the subscript, so I write phi of z instead of phi sub tau of z. Okay, please remember that the tau is there in the background, right. So I get this. Now why did I do this? What is the advantage of doing this? The advantage of doing this is, you see, I wanted to prove this differential equation, alright, and as I told you, the key to proving this differential equation is by looking at the Laurent expansion at the origin for the phi function. Okay, and of course the Laurent expansion of the at the origin for the phi function has this as a singular part and this is the analytic part, but you need to write this, since this is an analytic part, you see this is going to be a power series in z. Okay, and of course we have also normalized the phi function so that the constant term is 0. Okay, so this is going to be an analytic function, and the Weierstrass phi function is an even function, therefore if you expand this as a power series in the origin, you should get only even powers of z and you will get some coefficients, and the point is how do you write out those coefficients. Okay, so the fact is that from this expression directly it is not easy to write it down, but it is easy to write it down from this expression and from the Laurent expansion of this at the origin, which is quite easy to compute, because the Laurent expansion of 1 by z minus omega can be written out using the geometric series. Okay, so the whole point of this argument is you write out the Laurent expansion of zeta of z at the origin using the geometric series, because this is the term that will give you the expansion, alright, and then you and mind you if I look at the Laurent expansion of this at the origin, this will be the singular part, okay, and this will be the analytic part, but this analytic part is now easy to write because 1 by z minus omega can be expanded using a geometric series. Okay, so therefore to put it all together, it is easy to write down the Laurent expansion for zeta at the origin, and once you know that, and once you know this, that the negative derivative of zeta is actually the phi function, you can get hold of the Laurent expansion for phi at the origin. Okay, so this is the reason for having introduced this function. All right, so let's try to get the Laurent expansions. So you see, so you know, of course, if so, let me look at only this part of the only that part of the summation. All right, so that is 1 by consider 1 by z minus omega, okay, plus 1 by omega plus z by omega squared, take this, okay, and what you do is that you assume that mod z say is less than mod omega, okay, you assume this, so that well, in other words, mod z by omega is less than 1, okay, so that I can apply the geometric series. So what happens is that this term, you know, as usual, you can rewrite it as 1 by, well, minus 1 by well, 1 by omega into 1 minus z by omega, no, this should be omega times 1 minus z by omega, okay, you can write it like this. I mean, this is the usual trick that you use to get hold of series expansions using the geometric series. So if I write it like this, I will have to bring in a minus sign above, all right, and then of course the other two terms are 1 by omega plus 2 by plus z by omega squared, okay, and of course when I am certainly z is not equal to omega because mod z by omega is less than 1, right, and then this is minus 1 by omega, and if I expand this, I will get by geometric series, I will get 1 plus z by omega plus z squared by omega squared and so on. The general term will be z power m by omega power m, okay, I will get this plus 1 by omega plus z by omega squared, okay, and you can see that this 1 by omega is going to cancel with this the first term minus 1 by omega, and this z by omega squared is going to cancel with minus the second term which is minus z by omega squared. So what I am left with is minus of, you know, z squared by omega cube plus z cube by omega power 4 and so on. The general term will be z power m by omega power m plus 1 and so on, okay. So this is very easy to write down. So I am just writing down the the analytic part of the Laurent expansion of zeta of z at the origin, okay. The singular part is of course is 1 by z, right. Now what you do is that, well, so now you use this computation to get hold of the Laurent expansion at the origin for zeta, and how does one do it? So what one does is one takes zeta of z minus 1 by z, okay. Now this difference is actually the summation of terms, each of which we have expanded, okay. So what you can do is that you can write this difference as well, so that I do not make a mistake in signs, let me look at what I have written down. So it is yeah, so I write it as minus so this is going to be remember 1 by z is the singular part of the Laurent expansion at the origin, therefore this difference is going to be an analytic function, so it is going to be given by a power series, and I am just going to write as minus gm z power m, okay, and of course I will have to put a summation. So I am going to put a summation over yes, so I will have to write, so let me write this clearly. So minus summation over omega in the lattice omega not equal to 0 of these of terms like this, correct. So I will get a series here okay. So this is what I will get, alright. Now well, I write this as so I write it as only powers of z, okay. So if I write it as powers of z, I write as g sub m, so and I write sigma m equal to 2 to infinity, and I'll put a minus sign outside and put z power m, okay. So let me write it like this. So this is going to be you can see that see when I am summing over each of these omegas, okay, and for each omega I get z squared, z cube and so on, alright. I can sum it the other way. So what I can do is I can keep z squared fixed, okay, and take the summation over 1 by omega cubed, okay, and then absorb that as a constant which depends on tau essentially, okay. So I can write it in this form, okay. But the point is there are 2 points to be observed. I just want to say that here only odd m will survive, even m will not survive, because the quantity on the left side is odd, because you see if I change z by minus z, okay, I can pull out a minus sign from here, and I can also pull out a minus sign from here. So that means that when I expand it in the form of a power series, okay, I should have only odd powers of z, right. So because of that, you know, I can actually write it as sigma minus of sigma m equal to 1 to infinity, okay, g sub m z power 2m minus 1, okay. Now I am rewriting it only in terms of odd powers of z, namely z cube, z power 5 and so on. That is because if you sum over if you keep z squared for example and sum over all the coefficients, that will become 0, it has to become 0, okay. Similarly you do it for any other even power of z, all the coefficients if you sum it has to be equal to 0. The reason is because the left side is an odd function, and therefore you cannot have even powers on the series on the right side, okay. This is essentially a use of the identity theorem for power series, which says that 2 power series are equal if and only if all the coefficients are equal, okay. So in fact if 2 power series, convergent power series are equal on a set which has a limit point at which also the power series converges, even that is enough to ensure that the power series, the analytic functions defined by those power series are everywhere equal, and therefore the coefficients of the power series have to uniquely be related to, they have to be the Taylor coefficients, okay, for the Taylor expansion of that function, right. So therefore you see here I am switching from writing all the terms to only the odd terms, and what are, so what is this g sub gm, so let me write it out. Gm turns out to be so this gm, so where g sub m turns out to be so it will be summation 1 by 2 power m summation over omega the lattice, omega not equal to 0, 1 by omega to the 2m, okay, yes, this is what it will be, right. You can see because when there is an odd power you have to sum over omegas of one power more, okay, so it will be in this form. So if it is 2m minus, if it is z power 2m minus 1, the term below will be z power omega power 2m, and then you have to sum over all those omegas. So this is what you will get, but the point here that we are cleverly using is that the m's for even m, okay, they do not survive, they are all 0, okay, that is because of the oddness of the function on the left side, okay. So we get this, so let me write it out. So you get zeta of z is equal to 1 by z minus sigma m equal to 1 to infinity gm z power 2m minus 1, okay. I wonder whether I have put the summation correctly, because the first power that I should get is z3, which means I should start only with 2, so I have to be careful here, I have to put 2 here, okay. So please, there is no z term, there is only a z cube term, right. So here also I should be careful, okay. So it is m equal to 2 to infinity. So this is the so now you see we have a nice Laurent expansion for zeta in a neighbourhood of the origin. It is nice because you see the singular part was already known, it is 1 by z, it was the analytic part for which we wanted coefficients in a nice way, and that we are able to get, okay. Now how do you use this to get a Laurent expansion for the phi function? You just make use of the fact that zeta is an antiderivative for phi, okay. So you take the negative derivative of that, and because that is going to be again you know uniformly convergent series, you can differentiate term by term, alright. So as a result what you will get is this Laurent expansion of zeta at origin gives a Laurent expansion of phi at the origin just by term wise differentiation. So what I will get is phi of z is equal to minus zeta prime of z. So what I will get is minus of, if I differentiate it I will get 1 by minus 1 by z squared, and then I will get minus sigma m equal to 2 to infinity, I will get 2m minus 1 gm z power 2m minus 2. So you get it very easily, and so this turns out to be 1 by z squared plus sigma m equal to 2 to infinity 2m minus 1 into gm z power 2m minus 2, okay. Now you see between the original description of the Weierstrass phi function and this, you see now the analytic part is very neat. You have all the coefficients of the even powers of z. Of course you will have only even powers of z because this is an even function, okay, but the coefficients were not clear, so you get the coefficients in a nice way, right. Now once you have these coefficients one can write down a set of inequalities. So I am just worried about a sign somewhere. Okay, so what one does is that one can differentiate any number of times. So what one does is just one differentiates, okay. So we are not very far away from establishing the differential equation that we want, that the phi function, Weierstrass phi function satisfies. So the first thing you do is you differentiate, and of course write only a few relevant terms, okay, and it will be clear why these terms are relevant So let me write them here. So phi of z is, well, it's 1 by z squared plus, well, the first term if I put m equal to 2 I am going to get 3 g2 I will get 3 g2 z power z cube, okay, if I put m equal to 2 no z squared, okay. Of course I should not get z cube, I should get only even powers of z. So then I will write maybe I will write one more term, that the next term is going to be, I put m equal to 3 I will get 5 g 3 z power you see 4 plus other terms, okay. And why I put dot 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 is because those terms are not going to matter in my calculation, okay. So this is phi, then I calculate the derivative phi prime of z, okay. If I calculate the derivative I end up with well, I will get minus 2 by z cube. I can do term by term differentiation because this is a uniformly convergent power series, I mean uniformly convergent Laurent series, and I will get 6 g2 z plus 20 g3 z cube. Yeah, I stop with that, I am not worried about higher order terms, okay. Then I calculate the square of this p prime z the whole squared, I calculate this and I will get, well, 4 by z power 6 is one term. Then I am going to get I mean the terms that I am interested in are the I am essentially interested in the singular part plus say the constant term, alright. So I will get 4 by z power 6 and then I will get well, I will get minus 24 g2 by z square, okay, or is it I think it will be, yeah, z squared, that is a product of this term, these two terms multiplied by 2, and then I will also get so I will get a minus 80 g3 and then I will get the higher powers of z and so on, and of course this term is by, you know, by taking the product of these two terms in the square and then multiplying by 2, so I get this, alright. Then I also calculate 4 phi prime of z no, rather 4 phi of z cube, this is what I want, and this turns out to be, well, if you do it by hand it is 4 by so phi of z is this, if I take phi of z the whole cube I will get 1 by z power 6 and 4, so I will get 4 by z power 6, okay. You can see the reason why I am doing this, because you see I can, if I subtract then this coefficient goes away, okay, it is quite magical, rather God given somehow. Then the next term is 36 plus 36 g2 by z squared, okay, and one more term plus 60 g3 and so on, and these are of course higher order terms involving z squared and so on, alright. So now if you calculate and also calculate 60 g2 times p of z, which is going to give me 60 g2 by z squared plus so I am really not, see in the last 3 equations, in the last 3 expansions I am really not interested in the you know terms involving z squared, z power 4 and so on. Now what I do is, you know, I just take this minus this plus this probably, and then I'm so I take p prime z the whole squared minus 4 p of z cube plus 60 g2 p of z. If I calculate this, okay, okay, so if I calculate this, then what I end up is, of course, you see here this minus this, so the 1 by z power 6 is going to go away, term is going to go away, and then you see this minus this is going to be give me minus 60 g2 by z squared, and if I add it to this plus 60 z2 by z squared, so the 1 by z squared term is also going to go away. So finally I will get minus 80 g3 minus 60 g3, which is minus 140 g3. So what I will get is, I will get this is equal to minus 140 g3 plus some terms which will involve z squared and z power 4 and so on. Okay, now here is the beautiful point. The beautiful point is, you see the function on the left side is a doubly periodic function. The function on the left side is a doubly periodic function, which is in principle, you see phi is meromorphic, so you expect this side, you do not expect this side to be holomorphic, but on the other hand it is equal to the right side. The right side is holomorphic. See, the right side is minus 140 g3 plus some power series involving even powers of z. So what you have got is, you have got a doubly periodic function, okay, the left side is a doubly periodic function because phi is periodic, phi is doubly periodic with periods 1 and tau, and that is equal to a holomorphic function. This is what you are getting, okay. But you see, we already know a doubly periodic function which is holomorphic has to be a constant, okay, by Liouville's theorem, right. So LHS RHS LHS doubly periodic and RHS holomorphic imply that LHS is equal to RHS, the left side is equal to the right side is equal to a constant. This has to be a constant, okay, and what is that constant, and what is that constant? That constant can be evaluated by taking the right side and substituting z equal to 0. If I take the right side and substitute z equal to 0, I will simply get 1 minus 140 g3, so that constant will be equal to minus 140 g3. So what is the upshot of this? The upshot of this is that we have the following differential equation, which is what we wanted to prove. So the upshot of this is that the Weierstrass phi function satisfies the following differential equation. Let me just check that the sign is, I am supposed to get a, there is a, so I think yeah, minus 140, so which is what I wrote as 4 times p of z the whole cube minus g2 p of z minus g3. So you get this differential equation, okay, which is what we wanted to show, right, where of course I have put small g2 as 60 times capital G2, and capital G2 is summation over all non-zero lattice points of 1 by omega power 4, okay, and G3 is 140, small g3 is 140 times capital G3, and capital G3 is summation over all non-zero lattice points of 1 by omega power 6, okay. So you get this nice differential equation, okay. So that was the aim of this lecture. So we in the forthcoming lectures I will explain how you use this information to get hold of a function on the upper half plane which is going to be invariant under the action of the unimodular group, namely a function which will try to give you an invariant for the tori, okay. So we will see that in the forthcoming lectures.